We want to see what yield line theory of plates is. We'll start with the introduction. You go to limitations for elastic analysis, yield line theory for plates, yield lines themselves, and basic principles of yield line theory. Yield lines are indicators of large deflections in thick ductile plates. An example of a thick plate that can undergo yielding is a reinforced concrete slab. There are certain limitations of elastic analysis of slabs, and one is that slabs panels are square or rectangular. One-way panel slabs, they should also be supported in a specific way. For reinforced concrete slabs, there is sufficient justification for adopting the inelastic analysis, as evident from the limitations of the elastic analysis. So the above assumptions, which we have talked about, are not always the case as illustrated in this figure below. So, for example, if you have a slab that is not rectangular, you see that's semicircular, and it is not even simply supported, it's clamped on two adjacent sides. When you have rectangular and they are clamped along two adjacent sides, and one side is free, and there could also be a column, and this other side is free, then the elastic theory assumptions will not hold. You could also have a circular slab supported on columns only, as shown on this diagram C. You could also have a rectangular slab, but simply supported on two adjacent sides with a partition, as shown in diagram number D. That figure, which I'm calling figure 1, we are showing different types of slabs. I have talked about a clamped circular slab, clamped rectangular slab, circular slab supported on column supports only, and this simply supported rectangular slab. Therefore, for slabs of triangular, circular, and other plan forms, and for loads other than uniformly distributed, and for supports conditions other than those specified in figures 1A to D, which I've already shown in the previous slide, and for slabs with large openings, we find that the collapse limit state analysis has been found to be a very powerful and versatile method. Now, inelastic or limit state analysis is similar to the plastic analysis of continuous steel beams, which is based on formation of plastic hinges, which enable the formation of a mechanism of collapse. However, full plastic analysis of reinforced concrete beams and frames is tedious and time-consuming. One important advantage of the reinforced concrete slab over reinforced concrete beam and frames is that the slabs are mostly under-reinforced, and this gives a large rotation capacity for the slabs, which may be taken as the presence of sufficient ductility. It is assumed that during the rotation, the bars within the concrete remain in their original direction and they don't suffer kinking. The yield line analysis is also valid for slabs that are not of reinforced concrete, the slabs which undergo ductile behavior. Therefore, for both reinforced and unreinforced concrete slabs, the Johansen stepped yield line criterion states that yield line is actually made up of many small steps in orthogonal directions. Yield line analysis was pioneered by K.W. Johansen in the 1940s, and it is only applicable to ductile or other reinforced slabs, since we assume that the moment rotation diagram shown in figure 2 below holds. The moment rotation diagram, this is the moment, this is the curvature, and the first crack, you can see that line, which I'm showing with my cursor. There is the first crack forming, and beyond that level, you find that you have the curve of a deformed bars or mild steel. Mild steel behaves that way, where you have the elastic range and the plastic range. Then if you have a curve that goes beyond F and then a horizontal line, that is characterization for mild steel. The first one was deformed bars. Deformed bars undergo that kind of a curvature. The mild steel undergo elastic, then there's elastic limit, and then you undergo a plateau, plastic plateau like that. When you have idealized, the idealized case is where you go soon after the elastic limit happens. Then you have the plastic plateau. And this is still the moment curvature. For the idealized, you have a straight elastic, and then it goes into a plastic deformation. So the real cases are shown there. And in this diagram, you find that this area is the elastic curvature. The elastic curvature around there, and then you have the plastic curvature. So you have two portions. Ideally, you have the elastic and the plastic curvature. Yield line is closely related to the plastic collapse or limit analysis of steel frames, and it's an upper bound or mechanism approach. Yield lines are lines of maximum yielding moments in other reinforced slabs. The yield line theory thus is an ultimate or factored load or collapse limit state method of analysis based on bending moment on the verge of collapse. At collapse loads, the slab begins to crack as they are mostly under reinforced, with the yielding of reinforcement at points of high bending moment. With the propagation of cracks, the yield lines are developed gradually. Finally, a mechanism is formed when the slab collapses due to uncontrolled rotation of members. Yield lines, therefore, are lines of maximum yielding moments of the reinforcement slab. The essence of yield line theory is to find out the locations of appropriate yield lines. It is therefore, in summary, important to note that only under reinforced bending failure is considered in this theory, ignoring the effects due to shear, bond, and deflection. So we just look at the bending failure and ignore the effects due to shear, bond, and deflection. Also ignored are the effects of in-plane forces developed. So what we look at next is virtual work and yield line theory. Application of virtual work. Let's look at a clamped slab. Consider a rectangular slab of size L1 times L2, L1 times L2, and it is fixed at two opposite ends as shown. This end is fixed, that one is fixed, and these ones are free. The collapse load will be applied loading W multiplied by a factor lambda C, lambda C times W or lambda times W is the collapse load. So W is the applied load, that's the factor. And the factor is applied for safety to make sure that the load we are calculating is the true collapse load. Now, the conditions during collapse are such as to develop enough plastic hinges to make the structure a mechanism. For example, for the rectangular slab we are discussing, which is fixed at two opposite sides, the collapse condition is represented by a hogging and a sagging moment, yield lines, due to the corresponding collapse load, which has a factor. So the dashed line is the hogging moment over there, and the zigzag is the sagging line. That's the convention we use, and the hatched edges are fixed, and the straight line are free ends. the rotation of a slab at collapse, the amount of rotation theta is shown in the figure below. Note that at the middle span hinge, the rotation will be 2 theta. So if that is theta, okay, this is the direction L1, and therefore there will be the yield line, and as shown, where we have the hogging moments and the sagging moments, the angle thetas, and at the middle, there will be that angle theta and that angle theta, and therefore the total rotation will be 2 theta. That's what we mean by the rotation will be 2 theta at midspan. The external work that is done by rotating or by developing these yield lines will be equal to the internal work done at collapse. And the external work will be done, which is the total load on the slab times the average displacement it will move through. And the external work, of course, will be balanced by the internal work. The internal work is the moment capacity of the plastic hinge, which we call M-L2 and ML2 times the rotation it moves through. So the M dash and M are used to denote the hogging moment, M dash, and the sagging moment, M. And the external work done will be equal to the collapse load times the distance moved, the average distance moved, as shown. If you look at that equation, that's the external work on the left. The internal work will be done through the rotations at the plastic hinges, as shown. There will be a rotation on the left-hand side, and there will be a rotation at midspan, and there will also be a rotation on the right-hand side. You can see M dash, the hogging moments, will be applied at the left-hand side and at the right-hand side. And of course, the sagging moment, M, will be at the midspan. And L2 is the longer direction. We'll see whether that's correct. Just check whether it's the shorter or the longer direction. I think these two is the shorter and the longer. You correct that, no problem. Then you find that the yield line, there are guidelines to draw the yield patterns, and that has already been covered. I'm just repeating. So location of the axis of rotation. One, the yield lines between two intersecting planes are straight lines. Positive yield lines will be at the midspan of a one-way simple supported slab. Negative yield lines will occur at the supports in addition to the positive yield lines at the midspan. Yield lines will occur at the point loads. Yield lines between two slab segments should pass through the point of intersection. And continuing, the yield line should end at the boundary of the slab. They should represent the axis of rotation. Supported edges of the slab will also act as axis of rotation. And axis of rotation will pass over any column support. And this is shown in that illustration of the diagram. You can see the zigzag lines are the yield lines within, and the different types of patterns are as illustrated. If you have a column, for example, on a slab, then you see the yield lines you have to intersect as shown. So these are the axis of rotation as shown. Axis of rotation, you have to input the axis of rotation. And also if you have different types of slabs supporting, the supporting methods are different. For example, you can see that one, two adjacent sides are supported and another two adjacent sides are free. Then I have also indicated here what is incorrect and what is correct. When you look at that particular illustration carefully, it will help you to come up with the yield patterns, because the yield patterns are the ones which will help us to work out the work done, to interpret the collapse as accurately as possible. So identifying and drawing yield patterns correctly is a major part of yield line analysis. There are conventions, we've already done them. The sagging yield lines are solid wavy lines. Hogging yield lines are dashed straight lines. A fixed support is indicated by double hatching. A simple support is given by a single line hatching, and a free edge is given by a straight line. So these are the conventions we have already used and which are normally adopted as conventions for yield lines. The moment axis notation also from the figure below, the reinforcement in the x direction provides moment capacity of mx parallel to the y-axis. So that's the moment capacity. If your slab has bars in the x direction, the moment capacity then will be shown as mx. Thus, any yield lines parallel to the y-axis will be opposed by x direction reinforcement. So if you have a yield line there, then of course, they'll be opposed by the reinforcement in the y direction. And the same goes for yield lines in x direction opposed by my capacity of the slab. So if you turn the direction of your reinforcement, then the yield line in the x direction will be opposed by the reinforcement in the y direction. And this is also a moment capacity as well. And if you have an arbitrary angle, if you examine the case of an orthotropic slab, that is, has different moment capacities in different orthogonal directions. This is usual for reinforced concrete slabs. And isotropic slabs are a particular case in which mx is equal to my. Okay, this is a special case. Thus, we will have moment capacity per meter mx on the x face and moment capacity per meter my on y face, as shown in the figure below. So this is a special case of if you have an isotropic slab, a special case, you have mx equal to my. But normally you have this kind of an arrangement or dimensions of the slab where mx and my are not necessarily equal. So the moment capacity also at an arbitrary angle. The figures above illustrate how the moment capacity is obtained for any other direction, alpha. If you have a direction alpha, the moment capacity in that direction is obtained by resolving the vectors as shown in diagram number B. So we have our vectors representing, and then we resolve these vectors as shown, so that you have m alpha L is equal to mxl sine squared alpha plus myl cos squared alpha, and thus the moment m alpha, the moment in direction alpha, will be given by mx sine squared alpha plus my cos squared alpha. So I thought it's important for us to get that right from the word go, so that when we are thinking about the moments, resistance of a slab due to reinforcement, you look at it from different directions. And remember, this moment capacity is the one that will be used in design. So we have looked at virtual work and yield line theory. And the next one we'll look at is the method of segmental equilibrium. Slab, statically determinate slabs, statically indeterminate slabs, assumptions of yield line theory, guidelines for yield line pattern, lower and upper bound theories. As an introduction, we have, first of all, the limitation is that it's subjected to short-term loading. We look at statically indeterminate slab, statically indeterminate and statically indeterminate. And we'll be looking at the elastic analysis itself. For the statically determinate slab, you note that if it is statically determinate, then this is the slab, okay, with the size AA, BB, AB, and AB down there. The two opposite sides are simply supported. And if we were to load, give it a loading, shown as that, then the section unloading and deformation and curvature distribution will be as shown with the simply supported. So if you look, for example, at this arrangement of a slab, then the yield line will be at the point of the maximum bending moment as shown. And if you look at the section and loading deformation and curvature distribution, there is a section between D and E where you have your curvature values are shown. Between those two areas, we are able to define the curvature there and the angle subtended there, phi P over there. And we also have phi E. Okay, this is a plastic, that's the elastic. That just is an enlarged curvature where you have the maximum strain there. X is the distance to the neutral axis, and that's the angle phi. If you look at it from the strain diagram of a rectangular section. Then down here, if the load keeps on increasing, then up to the yield line at point C, then you have your plastic moment. So there'll be a hinge there. And the sides, these sides, AC and CB, will be elastic segments. That's the bending moment diagram for the elastic stage, the simply supported one way. For the statically indeterminate slab, you have the yield lines, a positive yield line in the middle and negative yield lines at the supports as shown, at the clamped supports. If this is the section, then it's fixed there, clamped at A and B as shown, and it's a one-way slab. The other diagrams of interest is as the load is increased. You find that the load here is referred to as load W1, and this load here, W1, will be such that the maximum load in the middle is W1 L squared over 8, and the plastic moment will be greater than that moment, elastic moment. If we increase the load and have a load as W2, whereby now you have a plastic moment at the supports MP, the bending moment diagram is shown as that. This is the deflection diagram with a plastic hinge at the ends. Then the bending moment and deflection diagram are such that the load W2, the moment MP, the plastic moment MP at this stage, when the load has been increased to W2, the MP will be equal to the WL squared over 8, as shown. So MP and that load will be the same. We are assuming, of course, that the reinforcements at the support and the span are the same. If we increase the load further to W3, sorry, then you'll find that there'll be these hinges, 3 hinges you form at A, C, and B, plastic hinges you form. And the bending moment diagram will be with a load W4, and W4 L squared over 8 will be greater than MP, okay? And it showed like that. So as you increase the load, then you find that your system, your value of the loading keeps on increasing such that W1 is less than W2, less than W3, less than W4. And basically, that is the state of a mechanism. So a clamped one-way slab can sustain the loads without collapse, even after the formation of one or more yield lines. And the bending moment and deflection diagram of the slab with increasing loads, we've already looked at them. During the elastic range, the negative moment at the clamped edge is W1 L squared over 12 and is twice the positive moment at midspan, okay? Which is W1 L squared over 24. Now, assuming that the slab has equal reinforcement for positive and negative moments, the highly stressed clamped ends start yielding first. Now, though the support line hinges rotate, the restraining moments continue to act till the midspan moment becomes equal to the moment at the supports. Accordingly, a third hinge is formed. This is just an explanation of what we have already seen in the previous diagrams. And it is clear from the above discussion that mechanism is possible in the bending moment diagram of the load equal to W4 if the slab is having adequate reinforcement to resist equal moments at the support and midspan. The elastic moment ratio of 1 to 2 between the midspan and support could be increased to 1 to 1 by the redistribution of moment, which depends on the reinforcement provided in the supports and midspan sections. What are the assumptions of yield line theory? 1, the steel reinforcement is fully yielded along the yield lines at collapse, and rotation following yield is at constant moment. Number 2, the slab deforms plastically at collapse and is separated into segments by the yield lines, and the individual segments of the slab behave elastically. Number 3, the elastic deformations are neglected and plastic deformations are only considered. The entire deformation, therefore, takes place only along the yield lines. The individual segments of the slab remain plane even in the collapse conditions. Number 4, the bending and twisting moments are uniformly distributed along the yield lines. The maximum values of the moments depend on the capacities of the section based on the amount of reinforcement provided in the section. Number 5, the yield lines are straight lines as they are lines of intersection between two planes. Now, the guidelines to draw the possible yield patterns. You remember in the simply supported and the clamp slab, we just assume because we happen to know the bending moment diagram and the positions of the maximum moment. And of course, then we know that's the areas that you yield first. But we need to have guidelines. Number 1, the yield lines between two intersecting planes are straight lines. Number 2, positive yield lines will be at the midspan of one-way simply supported slab. Number 3, negative yield lines will occur at the supports in addition to the positive yield lines at the midspan of one-way continuous slabs. Number 4, yield lines will occur at a point load and they will be radiating outward from the point of application of the point loads. Number 5, yield lines between two slab segments should pass through the point of intersection of the axis of rotation of adjacent slab segments. Number 6, yield lines should end at the boundary of the slab or at other yield line. Number 7, yield lines represent the axis of rotation. Number 8, supported edges of the slab will also act as axis of rotation. However, the fixed supports provide constant resistance rotation, having negative yield lines at the supported edges. On the other hand, axis of rotation at the simply supported edges will not provide any resistance to rotation of the segment. Number 9, axis of rotation will pass over any column support if provided, whose orientation will depend on other considerations. Now, there are two theorems. There is the lower and upper bound theorems. According to the general theory of structural plasticity, the collapse load of a structure lies in between the upper bound and lower bound of the true collapse load. Therefore, the solution employing the theory of plasticity should ensure that lower and upper bounds converge to the unique and correct values of the collapse load. What is the lower bound theorem? The lower bound or the true collapse load is that external load for which a distribution of moments can be found, satisfying the requirements of equilibrium and boundary conditions so that the moments at any location do not exceed the yield moment. What about the upper bound theorem? The upper bound of the true collapse load is that external load for which the internal work done by the slab for a small increment of displacement, assuming that moment at every plastic hinge is equal to the yield moment and satisfying the boundary conditions, is equal to the external work done by that external load for the same amount of small increment of displacement. So in summary, the collapse load satisfying the lower bound theorem is always lower than or equal to the true collapse load. On the other hand, the collapse load satisfying the upper bound theorem is always higher than or equal to the true collapse load. So in the yield line analysis, the yield line analysis is actually an upper bound method in which the predicted failure load of a slab for a given moment of resistance may be higher than the true value. Thus, the solution of the upper bound method or yield line analysis may result into unsafe design if the lowest mechanism could not be chosen. However, it has been observed that the prediction of the most probable true mechanism in a slab is not difficult. Thus, the solution we get by using the upper bound theorem is safe and adequate in most of the cases. However, it is always desirable to employ a lower bound method, which is totally safe from the design point of view. After predicting the general yield pattern and locating the axis of rotation, the specific pattern and locations of axis of rotation and collapse load for the slab can be determined by one of the two methods below, either the method of segmental equilibrium or method of virtual work.